Hello again, ladies and gentlemen. For our last example of an object shot horizontally, we've got actually two objects. There are two objects initially the same height above the ground. Simultaneously, one is released from rest, like so, and the other is shot off with a horizontal velocity of 2.5 meters per second toward the other. We know that that one's motion is going to be something like so. The two objects collide after falling 20.0 meters. How far apart were the objects initially? So we've got these objects here, okay? And one of them falls while the other one is shot horizontally, and they collide somewhere. Okay? We've got to figure out some things about this. So let's get my object 1. Object 2. Object 2 is going to fall straight down. Object 1 shot horizontally, and this is where they collide. It's such a collision that you can't even see the objects. It's so bright. Okay. Now let's take a look at what we know about this. Okay. They're initially the same height above the ground. So, well, we're not interested so much about the ground, we're interested so much about where they collide. Okay, so y is the same for both of them. We can say y1 equals y2, but might as well just call it y at this point, right? Okay, simultaneously one is released from rest. Let's stop there because that tells us something. That tells us the initial velocity of this object. Vy naught is 0. So Vy naught for the second object is 0. Okay? The other is shot off with a horizontal velocity of 2.5 meters per second. So again, horizontal velocity, V naught at 1 is 2.5 meters per second. We already know that is the x velocity, the x component of velocity for the entirety of its trip. Okay. We also know that Vy naught for 1 is 0 again. Alright, the two objects collide after falling 20 meters. So, we know what this value is. This value is 20 meters. Okay. How far apart were the objects initially? So let's take a look at, well, how far apart they are. It's going to be an x value. Right? Okay. So this is what our question is about. Our question is about this x. Okay. Now in the x direction, we've got one equation to work with. Right? X equals the initial x velocity and the final x velocity and the average x velocity multiplied by the time. Well, Vx, got it, no problem. Time. We don't have the time. Okay? But what we can do is find it from our second situation here. Okay? Now, this one's going to be not quite as easy as we thought. We'll take a look at our equations and see what we can do for this from the y direction. Got y plus the average Okay, so here are our options in the y direction, and we need to solve for time. Well, let's see what we have to work with. We know the initial velocity is 0, so that will take care of some things there, and there. 0 for both of them. We know a y value, so, well, we'll make the initial y value 0, which means we know this one here. We know this one here. We can see pretty easily this one includes the average velocity, which means we need to know the initial and the final velocity in order to find that average velocity. That one probably not going to help too much. Okay, so well, let's not rule it out just yet, because we can find the final y velocity with this one. Well, the question is, do we need it? Y equals 1/2 gt squared. We know y, we know g, so we can find t fairly easily from that. Yeah? Alright, let's just go with that. Why go with a more difficult equation when an easier one will do? So if y is 1/2 gt squared, then t is the square root of 2y over g. In which case we know t. So let's just put that in. I'm going to rewrite this as x equals vx times t, which we know is 2y. Sorry, the square root of 2y over g. Knowing all of these values, we know the initial velocity in the x direction is 2.5 meters per second. We know the initial height was 20 meters, and we know the acceleration due to gravity. We can find x as a value of 5.0507 meters. Let's just 3 digits. And there you have the distance that these objects were apart when they first began their motion.